Okay, so welcome back to this next video in which we are discussing Cayley's theorem. Okay, so in the previous video what we saw is the motivation for Cayley's theorem. Okay, we are hoping to be able to answer the question of whether if you take an arbitrary group here, you can think of the symbols of the group as representing set permutations of some set, okay, and then the composition law is representing the composition of those set permutations. Okay, we know that we can build groups by thinking of the symbols as representing set permutations of some set, but is it the case that for any group you can always think of the symbols in that group as representing set permutations of some set? Okay, that's the question that we want to answer. Okay, and Cayley's theorem is going to give us the answer yes, basically. Okay, and to let a little bit of a cat out of the bag here, the set that we are going to see that you can think of every symbol as representing a set permutation of is actually going to be the set containing the symbols of the group itself. So you're going to copy this set basically and put it down here, and then you can think of all of the symbols in the group as representing set permutations on that set of symbols itself, basically. Okay, and Cayley's theorem is going to give us a way of doing this, basically, and this will be consistent with the composition law over here, i.e. the composition law here will represent the composition of those set permutations. Okay, however, before we can actually get onto that, there is something that you need to understand about the composition law within groups, basically. Some prerequisite knowledge, and I want to discuss that with you firstly. Okay, right, so what I want to discuss is two sets, basically. Okay, and firstly let me just give you the notation, and then I'll explain what these things really are, and then I'll explain the understanding that I want you to have. Okay, so we are going to look at something which is written little a, big G, like so. Okay, where little a is some element of the group. Okay, so we are going to look at a set which is called little a, big G for the group, and little a is some element of the group, and the way that this set is defined is that it's going to equal all things of the form, and I'll just move this up a little bit, A composed with G, where little g is an element of big G. Okay, so basically what you will do is you pick some element of the group, an element of your choice, okay? So you start off by picking your little a, and you can pick whichever element of the group you like, okay? And then what you do is you take that element and then multiply, well, you take every other element of the group and multiply it by this element a, basically. Okay, so here is our element a, and you are multiplying a, or composing a, I should say more abstractly, with every single element of the group, basically. So you go through every element of the group and you multiply it by a, and I will often use multiply and compose interchangeably. Okay, so you multiply every element of the group by a, and you collect all of the answers in a great big set, like so. Okay, and that is what is meant by a G, basically. Okay, it's all left multiples of the elements of the group by a, basically. Okay, right. So what I now want to do is give you a better intuition for what this set actually is, because there is a nice intuition for what this set is in terms of the composition table. So if I bring the composition table of the group back down here, okay, so here is the composition table from our group. Okay, and we have our element little a, which we have fixed. Okay, and let's say it's here. This is the row that's been dedicated to little a in our composition table here. Now, the nice interpretation then for AG, this set that I've just defined for you, is that what we are going to do is we are taking every little g as an element of capital G, and we are left multiplying it by a. Now, every little g is an element of capital G has a column dedicated to it up here, basically. Okay, so over here you will have every single element of capital G at some point along here. So every element of capital G will have a column dedicated to it. Okay, we know that. Now, if we want to take the set, which is all elements of the group capital G left multiplied by A, hopefully you can see that that is just this row of entries here. Okay, because what we're going to do is we're going to go through every element of capital G and we're going to left multiply it by little a here, and we will get the answer that's in this row basically. So for an arbitrary element, little g here, we'll get the answer a composed with little g, which is down here in the column dedicated to little g and in the row dedicated to little a. So if we're going through all elements of capital G, we will go through this entire row. So in fact, this set here is just all of the entries that are in this row. Okay, so you go along this row here dedicated to little a, and you take all the entries in that row and you stick it into a set, and that is what is meant by this set here basically. Okay, so all elements of the group left multiplied by little a, that's what's meant by AG, like so. Okay, right, so let me just now introduce you to another set which is a very similar idea, which is the other way round. So we'll have capital G now, and now we'll have A on the other side. Okay, so you might be able to guess what this is going to be. This is going to be all elements of the group right multiplied this time by little a. So in abstract notation, this will be little g composed with little a for all little g is an element of capital G. Okay, or where little g is an element of capital G. So what you'll do to build this set is you'll go through all elements of the group capital G and you'll right multiply them this time by little a, okay, which is your chosen element of the group. And you can do this for any little a, but you have fixed this little a when you are creating this set basically. Okay, and you'll put all of the answers into this set, and that's what is meant by capital G little a there. Okay, now again there is a nice interpretation of what this actually means in terms of the composition table, and I'll just label this one up here. This orange row here was AG. Okay, now if this was a row you might be able to guess what this is going to be, so let me draw out the composition table again. Okay, so this time we're right multiplying by little a, so we'll need the column dedicated to little a here. Okay, and once again, every element of the group, every little g is an element of the group, has a row dedicated to it this time. Okay, so what we are effectively looking at when we ask for this set is we're saying go through all of the elements of the group capital G here, and I'll just colour code that in. So here is all of the elements of capital G, and you are going to compose them or right multiply them by A basically. Okay, and that will give you all of the answers in this column basically. Okay, so once again I'll do an arbitrary element. So if we have an arbitrary little element little g down here, then you'll have the entry little g composed with little a here, okay, which is the row dedicated to little g and the column dedicated to little a. So when you construct this entire set, what it really means is this entire column in the composition table. So you go through all of the entries in that column in the composition table, put them into a set. That is what is meant by GA, like so basically. Okay, so that's just a bit of notation at the moment. What do I actually want to show you about these rows and columns in the composition table? Because that's the important bit of understanding that you need to have for us to explore Cayley's theorem any further. Okay, well here is the big thing. Basically, if this is a group, if this composition table is from a group, then it is the case that all of these rows in the composition table, and note, I didn't specify what little a was, so it could have been anything, so we could be talking about any of these rows here. Okay, all of these rows, which I'll call A, G, like so, actually contain every element of the group once and only once. So this set here, this is actually equal to the entire group. You get every element of the group back again when you do this. Okay, so when you take all elements of the group and left multiply them by some other element of the group, little a, and collect all of the answers in a set, you do get the entire set back again. Okay, so this is the entire set, and more than that, more importantly than that, if you actually look at this row here, you never get degenerate entries. You never get one element of the group appearing more than once. So not only do you get every element of the group appearing here, but you only get it appearing once, and that's what I want to show you. Okay, and it's the same for these columns. Every single column of the composition table only has every element appearing once, and it does have every element appearing once. So every element appears once and only once in every single column and every single row, basically. And that's what we want to show. So AG is equal to G and GA is equal to G for all little a is an element of capital G, which just says that this is true for whatever row and whatever column you actually pick in this composition table. Okay, so that's what I now want to show you. So we'll start off with rows, and then the arguments are almost exactly the same for columns, but we'll do them anyway. Okay, but we'll start off with rows. Okay, so there's two things we need to prove here. We firstly want to prove that no element appears more than once in this row, basically. Okay, so we want to prove that you can't have the same element appearing twice within this row. Then what we want to prove is that every element of the group does show up in this row, basically, and then we'll have shown what I want to show, basically, that this is indeed the entire group and every element appears once and only once. Okay, right. So we'll start off by proving then that no element can appear more than once. Now, how are we going to do that? Well, let's do it by contradiction. Okay, so let me just bring the composition table down here. I'll just draw it out again. Okay, so we've got our row here corresponding to the element little a. Now, let's suppose that it wasn't the case that every element appears once and only once. And let's say that we have an element appearing twice. Okay, so let's say that the answer here happens to be the same as the answer here. Okay, now for each of these entries you had to have some element of the group which when left multiplied by a gave those. So let's just fill this in. Let's say that we have some element little g which composes with a, or when you left multiply it by little a you get this entry here. So let's say, let me colour code this in. This entry here in red is little a composed with little g. Okay, now for this entry over here we'll have some element g prime, which is an element of capital G, such that when you left multiply it by a, you get the same answer. So we'll call this entry here little a composed with little g prime. Okay, and we are saying, okay, these two answers are going to be the same thing. We need to arrive at a contradiction, basically. Okay, because I'm saying this can never happen. Okay, but we're going about a proof by contradiction, so we're saying suppose it does happen, then it's true that basically little a composed with little g will equal little a composed with little g prime for some g and some g prime are elements of the group, basically. Now, why is that a contradiction? Well, what we can now do is compose on the left by a inverse. So let's multiply both sides by a inverse, and of course what we'll get is the a cancelling. So now what we'll end up getting is that g is equal to g prime. Now that's utter rubbish, okay, because we assumed that g and g prime were distinct elements in the group, and now we've just proven that they're the same element in the group. Okay, so that's basically a contradiction. So what I have just shown you is that if it was the case that you had an entry appearing more than once within a row corresponding to A, basically, then you can prove that these two elements that gave rise to those two entries were the same thing, but that's a total contradiction on them being separate in the first place. Okay, so it just is utter rubbish, basically. You cannot have an entry appearing more than once. So basically what we've just shown is that you can only have an element of the group appearing once in this entire row dedicated to A. Okay, you can never have an element of the group appearing more than once, and that's a fairly nice thing to know. That gives us a deep insight into the nature of the composition table for groups. Okay, each row only contains an element of the group once. It can't contain it twice. Okay, otherwise you get this blatant contradiction. Right, okay, so we've now proven that each element can appear only once. What we now want to prove is that every element appears at least once. Okay, so we want to prove that every element appears once and only once. We've done the only once bit, but we haven't yet shown that every element has to appear. Okay, now of course you can argue in the case of a finite group that we have shown that. Okay, because if this was a finite group, then the number of entries in this row has to be the same as the number of entries in the group. Okay, and since no element can appear more than once, every element has to appear once, otherwise you just would run out of things to put in the spaces, basically. Okay, however, we want to prove this for infinite groups as well, and in infinite group case, it's that sort of logic that works in the case of finite groups is no longer applicable. However, this theorem does hold true in the case of infinite groups, so we'll now do this proof, which will prove it for infinite groups and finite groups, but you could argue that we've already proven it for finite groups. Okay, so I want to prove that any element of the group has to appear once within any row, basically. Okay, right. So quite simply, let's take a little g as an element of the group. Okay, so I've taken an arbitrary little g as an element of the group. Okay, and I want to basically find you some other element of the group which, when left multiplied by a, gives you little g. So let me just draw the composition table out again. Okay, so I've taken an arbitrary element of the group and I want to find this within my row, basically. So if I just colour in my row here. Here is my row corresponding to A, and I want to prove that this arbitrary element of the group is in there. And since this was an arbitrary element of the group, if I can prove it's in there, then I've proven it for all elements of the group, basically. Okay, so I want to find little g somewhere within this row, basically. So what I would like to show is that there is some, let's call it little g bar, let's say, okay, such that A composed with little g bar is equal to little g. That's what I need to do. I need to find you this little g bar. Okay, so I need to find you the little g bar to show that there is a little g in this row, basically. Okay, so what do I then take for little g bar? Well, quite simply, here you go. Take little g bar is equal to A inverse composed with little g. Okay. So this is what I claim you can use as little g bar. Okay, so take little g bar is equal to A inverse composed with little g. Now little g is an element of the group. Okay, we know it's an element of the group because we assumed that. Okay, little a is an element of the group, so little a has an inverse in the group just by basic group axioms. Okay, so what I can do is I can compose little a inverse with little g to get another element of the group. Okay, because of closure of group composition. Okay. Find me this answer. You go away, calculate this answer, and call that little g bar. Use that as your little g bar. Okay? Now, if I then left multiply this answer by little a, what do I get? Well, the little a will now cancel with the little a inverse, and I'll end up with little g. Okay, so there is your little g bar. That's what you need to use, basically. Okay, find this answer, and then you've got something that you can compose with little a to get little g, and therefore little g must be an element of that row, basically. So we're done. Okay, and since we're just using an arbitrary little g as an element of the group, then this is applicable for all elements of the group. You can do this for all elements of the group, and hence you've proven that every element of the group has to appear in this row, basically. Okay, so what we've now proven is that every element of the group appears in this row once and only once, basically. Okay, and that's true for all rows of the group. Okay, and that's not trivial. Okay, that is a deep insight into the nature of the composition table on groups. We only knew that that was true initially for one element of the group, okay, which was the identity element, because we know that the identity element just composes with everything to give that other thing back again, okay, so it takes all elements of the group to itself, so you'd get a row which contained the entire group, just translated down a bit. But now we've done that, we've proven that this is the case also for every other element of the group, that all of these rows contain every element of the group once and only once, basically. Okay, and that's going to be a really important understanding for us to develop Cayley's theorem, basically. Okay, right, so for the sake of completeness now, let me do the same for the columns here, because the same actually holds true for the columns, that every element of the group appears once and only once in the columns, basically. Okay, so we need to prove the same things then. We need to prove that every element can appear only once, okay, so you can't have an element appearing twice. Okay, and we can use the exact same proof strategy as we used here. Okay, and I'll just get some more paper. Okay, so... Right, so now what we want to prove is that you can't have the same element appearing more than once in a column. Okay, so once again we'll do a proof by contradiction, okay, and this will just help solidify the arguments in your mind. Okay, so what we'll do is we'll consider the column corresponding to little a here, okay, and again, if there were two entries in the column that were the same, okay, so let's say these two entries here in the column corresponding to a were in fact the same, then what would that mean? That would mean that there had to be some elements of the group G which were right multiplying by A to give the same element. Okay, so let's call these little g and little g prime once again. Okay, and then these elements will be little g composed with little a and little g prime composed with little a. Okay, and we are now saying that these two elements are going to equal one another. Okay, so then what we get is that g composed with little a is equal to g prime composed with little a, and of course what we can now do is just right multiply by little a inverse. Okay, so that's the one change here, that instead of left multiplying by little a inverse, we instead need to right multiply by little a inverse. Okay, and then what that will reduce this equation into is that g is equal to g prime, and once again that's a contradiction because we assumed that these two were distinct from one another in the group, otherwise these wouldn't have been distinct from one another in the group. Okay, so we've arrived at a contradiction. We've shown that if these two are separate from one another, these two are the same, so it just can't work basically, it's just utter rubbish. Okay, so it can't be true basically that you ever have two entries in a column that are the same element of the group basically. Okay, so that's that proved that you can never have one element of the group appearing more than once in a column basically corresponding to any element of the group little a. Okay, so the other part then, we want to prove that every element of the group appears once in the column corresponding to the element A. So once again, we'll take an arbitrary little g as an element of capital G, okay, and what we want to show is that little g will appear in this column for little a. Okay, so here is the column for little a, and we want to prove that somewhere in this column little g is present. Okay, so we want to find, once again, a little g bar, which when you right multiply it by a, gives little g. Okay, so once again, my task is to find you this little g bar that we can use here, okay, to generate the little g here. Okay, so hopefully you might be able to guess what little g bar is going to be using what we did previously in the case of rows. Okay, so what I'll do is I'll set little g bar equal to little g composed with a inverse. So you can see that the technique is slightly different. We've had to make little modifications here to what we're doing because we're now doing right multiplication by a rather than left multiplication by a, but the spirit of it is exactly the same basically. Okay, so what I'm saying is, here is your little g bar. Take little g that you want to find in this column and compose it on the right with a inverse basically. Okay, A is an element of the group, so A inverse is an element of the group. G is an element of the group, so when I compose G with A inverse, I'm going to get another element of the group. Use that element of the group as your G bar, and my claim is that when you multiply this by little a, you must get back little g, because of course I could just express little g bar like so. Okay, that it is little g composed of a inverse, and then what must happen is that the a inverse must cancel with that little a just to give you little g back again. Okay, so that's how you can find this little g bar to use and right multiply by little a to find this element little g within your column basically. Okay, right. So that now proves then that all the rows of the composition table for a group and all of the columns for the composition table of a group contain every element of the group once and only once. Okay, and we will use this fact in the next video to discuss Cayley's theorem, basically.